Hello, class. Welcome to the next section, chapter 9.5. Today, we're going to be talking about methods in general for approaching integration. So, in chapter 9, we went over quite a few new methods of um, trying to integrate more involved, more difficult integrals. So, in this section, we'll just kind of look at a general strategy, as well as some other options for trying to calculate integrals that are too difficult to do by hand. Okay, so again, integration can be very challenging, right? It is much more difficult than differentiation, not in length, but just for the simple fact that there's integrals that are impossible to solve, okay, directly, meaning that you can't um, you can't solve them as a single function, right? You'd have to do some sort of numerical method, approximate the area under the curve, which is why we went over numerical methods, or you'd have to use a solver, right? So there are integration bees where mathematicians will come together and they'll have competitions for solving difficult integrals. So you get based on obviously for speed and for correctness, right? Um, let's just start off with a general approach to integration. Okay. Note that this is a fluid strategy. It's not like if this, do this, if this, do this. It's really just how to keep your eyes open for which approach is probably the correct approach. Um, when you may have to use several approaches, or when you might have to combine several methods into one. We've seen that in the last section quite a bit, actually, right? So it's not a defined methodology, right? To always find the correct approach. It's really just a tool to help us figure out what to try. Okay. So things to remember, an integral may have more than one method of solving. Okay. Some of these methods may be easier than others. We saw this with rotations, where we had the washer method and cylindrical shells. Sometimes one is better than the other. Um, but you have a choice when to use either one, right? So they can both work, but one might not work as well, right? Partial decomposition of fractions could be uh, also broken down into integration by parts, but one might be easier than the other to do, right? So keep a list of potential methods that might work. So on your scratch paper, as you're writing down, just jot down which methods you think might be applicable to this problem. Um, and then the ones that you know is not going to work at all. That way you cannot waste time working on those methods. Okay. Again, it's very possible that you must use more than one method at a time. So in the last section in partial fractions, there was a U substitution that we made, and then that U substitution turned into a partial fraction decomposition, right? We also saw an example where after partial fraction decomposition, we had to use a power function, a natural log, and a trig substitution in order to integrate the integram that we had simplified. Okay, so again, especially this last one, it's very possible that we have to use more than one method at a time for an integral. Okay, first thing we want to do is we want to simplify the integrand if we can. The thing that we're trying to integrate, if I can make it simpler, I will. Sometimes that means partial fractions. Sometimes this means rationalizing a numerator or a denominator. Sometimes this means just doing some very standard algebra, factoring even, right? So use techniques from algebra and any identities that we have from trig or identities from algebra to try to make the integrand simpler, right? We might have to use a trig substitution and then use that Pythagorean identity, that unit circle identity for trig, right? So there's lots of things that can happen. We might need a factor. We might need to complete the square, which we've seen. We might need to distribute. We might need to factor out a fraction, right? You've seen me do that quite a few times to make things easier to deal with. Sometimes we have to factor out a fraction. We might have to use an identity. Um, can I use an algebraic method to simplify to an identity? Then I can substitute something in. Um, I might have to rationalize the denominator, or I might have to rationalize the numerator. I might want to look for an equivalent form in the form of partial fraction decomposition. Um, and so those are the algebraic ideas. Okay. Number two, look for a substitution. Sometimes our first idea is to use a substitution and then we play around with it and we see it doesn't work. Sometimes I make a substitution and I can manipulate that substitution algebraically so that it does work. Again, in the last section, we saw something where we had to do that, right? So is there a substitution to change variables into trig functions that might make things easier in the world of trigonometry and angles of theta? Maybe the substitution doesn't look like it will help, but maybe I can manipulate that algebraically and make it work. Okay, so again, we saw that in the last chapter. Um, Number three, identify the form of the integral, right? This is something that I would probably want to use integration by parts on. Does it have the form of a function times a function? Or possibly is it a rational function where I can consider the numerator being multiplied by some sort of rational function? And then I do integration by parts, if it works well. Okay. Um, Trig integrals, right? Is there products or quotients of powers of trig functions? If there's quotients of trig functions, I can probably simplify somehow. If it's products of trig functions, especially powers, maybe I'm doing the trig identities, or I'm sorry, the trigonometric integrals. Trig substitution. Are there any radicals present? If there are radicals, do I see things that look like x squared plus or minus a constant term? So if you go back to that section, you'll notice that it was x squared plus or minus a squared. Here I'm just changing it just because what we're looking for is it x squared plus some number or x squared minus some number, right? And then the process is that number that we take, we then take the square root of and do all of our stuff, right? But what am I looking for? Is it some number? Is it x squared plus some number, right? Can we complete the square to get it to look like some sort of something squared plus a number, right? Something that looks like this. If I can get it to look like that, then I probably want to do some sort of a trig substitution like a or x equals a tan theta, right? Or square root a tan theta in this case. Um, Partial fractions, right? Am I integrating a rational function? Okay. Can I use long division there? Is the numerator have a higher degree or same degree as the denominator? Do I need to use synthetic division? Is the bottom function something that I can factor? Is it polynomial? Can I make a substitution that will turn it into a rational function of polynomials? Can I complete the square? And then number four is when everything fails, try again. Go back and start fresh with a different approach. Or maybe somewhere halfway into your attempt, you're like, I could try this or I could try that. Maybe you try to get yourself back there and then take the other route. Okay. So again, try with another method. So most of what you're going to cover in this section is just integrals, right? Just some difficult integrals. So try to be crafty in figuring out how to approach them. Okay. Another method that we use is integration using tables. So many people in let's say early 1900s, 1800s, they didn't have a whole lot to do. But to integrate a bunch of functions. And they made books and books and books and books of these. And there's entire volumes dedicated to the general form of integrals, right? Some of these books have about 12,000 entries. They're volumes, like literally volume one, volume two, volume three. So people really like integrals and they can be very difficult. So sometimes it's easier just to go to a table. Why should I do all this work if someone has already done it before? So I would go to the table and I would try to match which integral matches best with the one that I have. Okay. Whenever I give you something like this, like a classwork problem or an exam problem, um, I will either give you a list to work off of, especially if this was like an in-person class, which at this point it's not. Online, the problem will have the generalized form given to you, or it'll give you a few generalized forms and you have to pick the right one and then go ahead and do this. But I would not, for my online classes, since there's so many options, I'm not going to just leave you hanging. Um, but it is important to be able to figure out which form yours kind of goes with the best. Okay. So for my course or section of it, generalized forms will be provided when asked for anything using a table. Okay, so real quick, let's just look at what one of these tables would look like. We come here to the internet, we can literally just Google tables of integrals and things will pop up. So here on Amazon, you can see $67 is a book of tables of integrals. Doesn't say how many pages it is, but I'm sure it's a lot. Okay, so there's lots of places, right? Again, here's another book, $72 for nothing but a bunch of integrals. And so generally, in a calculus textbook will give you a small table, um, right, like this OpenStax, which I have a link to in my course, which we use as a supplemental text. You'd be given a list of something like, it's probably like 100 integrals, okay, 100 plus, 113. So if you have something that looks like this would be your generic answer, right? And so that's basically, and it goes by sections. If you're doing some sort of an inverse trig function, you can find the general form of your integral. If you're doing hyperbolics, um, exponentials, or logarithms, you can come here and find the general form, right? You'll have e to something times sine of something. Well, it will generally look like this then, right? So obviously they probably use integration by parts here, and then just finish solving it, and then they got their general form. So these are not a lot, but they're there, right? Generally, probably be up here somewhere with the basic integrals. You might get into some of this trig stuff, right? Just depends on what your uh, thing looks like. You go to like the list of integrals here on Wikipedia, you can see that it has several as well. Right? These are different lists of integrals, and they're just right. So here's a list of rational integrals, and again, this is a miscellaneous list, right? So Wikipedia has a ton itself, right? This could be very daunting. So we'll talk about how to use something like this right now as well. Okay. Often when we're using a table, we're going to have to do a little bit of work before being able to use the general form for the solution that's given to us. As you saw, there's a lot of stuff going on some of those questions. So let's go ahead and do an example, figure out what we mean, right? So here I'm going to give you the table form, which is x squared over square root x squared plus or minus a squared. So if we're going to do this by hand, it looks like we'd probably try to use some sort of a trig identity. I'm sorry, a trig substitution. That's the first thing that I would probably try here. But a U substitution might work here as well, right? But it doesn't really matter because our general form is given to us. So this x squared plus a squared gets repeated here with x on the outside and 1/2. If this is a plus, then this is minus. This is a minus, then this is a plus, right? It's an upside down sign change. Then 1 over natural log x plus square root x plus a squared. So not too much different, not too much work we'd have to do here. But based on what we're given, it looks like we would probably have to do something special here, right? So my x squared looks like it's an e to the t, right? Because then when I square, well, my x is an e to the t, and then when I square it, I would get e2 squared. My a looks like it's a 1. Here I got e to the 3t. It doesn't exactly match what I got here, right? Everything else matches pretty nicely, except for this, right? So over here, we kind of came to the conclusion that x equals e to the t would make this part fit with this part. So let's go ahead and make that as our substitution. Um, let's let u equal e to the t. Okay. When I differentiate both parts, I get du equals dt or et dt. Okay. And so um, now you might just be saying, well, when I plug in u, I'm just going to get all of the same stuff, right? So let's go ahead and break this e to the 3t apart, right? So now I have et dt, right, which is my du. So when I make my u substitution, now it matches identically with what's here. It's in something squared over square root u2 minus 1. And we got that because doing this du e to the t dt allowed us to pull out and lower this degree by 1 so that when I make my substitution, it matches with what I have. Okay, so I have u over u squared over square root u squared minus 1, which matches perfectly. So now I'll just replace all of my x's with u's and all of my a's with 1's. Since this is a minus, this will turn into a plus. Okay, so here a is 1, x is u. So let's go ahead and substitute everything in that we have. So I have 1/2 instead of x, I put u, square root u squared plus or minus 1. This is the minus, so if we're using minus here, we will use a minus here. There you go. Opposite sign here, 1/2 natural log u squared plus or minus 1 squared plus c. So now when we put the sign in that we need, I got the minus 1 here. This one is the opposite, right? And this one matches here. This one is always a plus. So I have my 1/2. My substitution for u is e to the t, right? Um, this one's squared. The u squared is e to the 2t minus 1, 1/2 natural log e to the t plus square root e to the 2t minus 1 plus c. So we had to do a little bit of manipulations to get my function to look the same. Then after I did that, I just plugging stuff in, right? So let's talk about computer algebra systems. There are many computer algebra systems, or CAS. Um, the TI 89s, was it the 92s? And I believe the Inspires as well with CAS have a CAS system. So um, you can, get a nice calculator and it'll do a lot of these things for you. These are basically computer systems that can solve problems algebraically, right? Computer algebra systems. There's numerous computer programs that work numerically. The differences between these two types of programs is that um, one can give you an answer like you'd expect out of math, and the other one will give you some sort of like numerical approximation. Okay. So one can give you a simplified function as a solution, and the other requires a function that needs to be evaluated. So you tell the program what the function is, and then you can plug stuff into it. But generally, it will give you only decimal values out, right? So it won't give you 1/2, it'll give you zero point 0.5. It won't give you 1/3, it'll always say 0.33333333, right? So um, there's numerical computer algebra systems, and then there's standard computer algebra systems. Okay, um, so there's numerical and I guess you call it object oriented, right? So many numerical solvers have the ability to solve simple algebraic manipulations as well. So a lot of times, a lot of people like to use numerical solvers, especially engineers and physicists, because it basically does everything that they need to do, and it could be within whatever tolerance that they need it to be. Mathematicians will generally look at computer algebra systems that can do algebraic manipulations on objects. Okay. Um, if you're in my class, right, if you're not just watching this because you're doing your own studies in math or for another class, in our Canvas course, there's going to be links to a bunch of different computer algebra systems. In fact, you can always just Google computer algebra system. Wikipedia has a nice list of computer algebra systems, which let's just go ahead and look at real quick. So we're here looking for computer algebra systems. If I go to Wikipedia, they have what a computer algebra system is. I like looking at the list of computer algebra systems because it'll give you an idea of some things that you can look for, right? Especially if you look at the cost, right? maybe looking at the latest stable release date will help you figure out if you want to find this one or not. For instance, Axiom was last kind of released in 2014, so maybe they're not really keeping up with it too much, or maybe it's complete and it doesn't need any tweaks, which is highly unlikely because there's many new versions of Windows by now versus 2014. This is 2024, by the way. Who knows when you'll be watching this video. At this point right here, but it's for tensor field theory, which is possibly something I don't need, right? So this is a nice list, right? It tells you what's free, what's not. There's some very uh, common ones here, like New Octave is very powerful. It's compatible with MATLAB. It's basically a free version of MATLAB. So if you're into math, MATLAB is something you want to learn. New Octave is basically a free version of that. Not as large or as strong, but definitely anything that you need as a student. Um, let's see. Maple costs money, right? It can be very expensive. Mathematica is expensive as well. If you have Raspberry Pi, you can get it free though. Let's see. Maple is the same as Wolfram Alpha. Maxima, I've used before, it's pretty good. Sage is free. This is very large and popular right now. Scilab is a good one. Um, there's a lot. Toolbox for MATLAB is useful. This is Python based. If you like Python, this might be easy for you to pick up. Wolfram Alpha, they have a free online version that people like to use a lot, which is pretty powerful, but the paid version obviously is much stronger as well, right? So, uh, Wolfram Alpha, okay, is a good site to be on. It does lots of stuff. I'm not going to show you how to do this, but this is a nice place to play around and, uh, and learn how to use. Okay. So, again, a quick online search can help you to find many computer algebra systems. The TI-89, as I said before, or equivalent is what I use myself. I use this. I have an app on my phone that's free that I use for all my calculations. Okay, so let's go ahead and do an example. Remember in chapter 9.2, we're doing the trig substitutions, and we calculated the integral sine squared of x times cosine to the fourth power of x dx two different ways. We use two different substitutions. We use the Pythagorean identity substitutions, the unit circle substitutions, and then we use the half angle substitutions for cosine times sine. Okay, and each way that we did, we got the same answer. Okay, and this is that answer: 1 over 16x plus 1 over 64 sine of 4x plus 1 over 48 sine cubed with 2 of x. If we used an online computer algebra system or one that we downloaded, okay, so in this case, I'm using Wolfram Alpha, the answer to this integral when I plug it in is 116x, that's the same. 1 over 64 sine of the 2x, which is not the same, minus 1 over 64 sine of 4x over minus 192 sine 6x. So there's lots of difference here. There's no cube term. The fourth term is negative instead of positive. So really what it looks like is that this sine cube term, they probably used the double angle reduction until there was no more cubes, right? So if I were to simplify this term, I would probably end up with this answer. Wolfram alpha does that automatically for us. This is as far as we needed to go. There's nothing wrong to us with sine cubed, okay? An alternative form is also given by Wolfram alpha to this, right? And this is that alternative answer, right? So here we have the 2x, 4x, and 6x. And in this alternative answer, notice that there is none of that. Everything is cosine sine of x's, cosine sine of x's, and some power, right? But there is no 2x's, 6x's, 4x's anywhere in here, right? So again, I'm sure all of these are equal and all of them can be found by the other ones, but sometimes the computer algebra system will give you an n an unnecessarily long and complicated answer. Okay, so all three of these forms are equivalent, but the answer that we come up with varies depending on the method that we use to come to an answer, right? So again, be wary of those pure algebra systems. I know students like to not do anything by hand. If the computer will solve it for me, let me just do that. That's cool and everything, but you have to learn how to do these, right? Your algebra has to be strong, especially if you're going into some sort of a math field, right? If you're in calculus too. So make sure you're working these things by hand and then maybe using Wolfram Alpha or whatever system to check that your work is correct. Okay. Newer, maybe this is a better option.